All right. Our second talk this morning is by Tudor Padurariu, and it's on Categorical Donaldson-Thomas theory, Symmetry, and beyond.
Yeah, thank you for the introduction, and thank you for giving me the opportunity to speak in this conference. So today's talk is about joint work with Yukinobu Toda from IPMU. All spaces considered will be over the complex numbers. And the plan today is to talk about certain categories defined using coherent sheaves, which are associated to moduli spaces on Calabi-Yau threefold. So, these are the general objects studied in Categorical Donaldson-Thomas theory, but I'll be focusing for most of the talk on the case of C3. So the main results would be about actually points on C3, so about the Hilbert groups of points on C3. So I'll begin by recalling or by giving an overview of Donaldson-Thomas theory. So Donaldson-Thomas theory started as an inverted theory of complex smooth threefolds. So you do not have to impose that the threefold is Calabi-Yau. But if you do not do that, you also need to have some insertions in order to get numbers, in order to get certain integers, which are some virtual counts of sheaves on your given threefold. And as I'll explain on the next slide, and actually basically for all the talk, if the threefold that you start with is Calabi-Yau, the theory has certain refinements that are interesting in their own right. So there is more structure there. So here I just recall the definition of Donaldson-Thomas invariant. So yeah, I'm working with Giesinger semi-stability, but one can also work with more general stability conditions. And if we assume that the locus of stable sheaves is proper, one has a virtual fundamental class. If you impose that your threefold is Calabi-Yau, the dimension of this virtual fundamental class is 0. So via the degree map, you get an integer, this Donaldson-Thomas invariant, which, as I said, is a virtual count, or you can think of it as a virtual count of a stable coherent sheaves with a given arbitrary character. Next. So the initial interest in the DT theory was via its connection to Gromov-Witten theory. So for certain supports, the moduli spaces relevant are spaces of ideal sheaves. And actually, also in the Calabi-Yau case, and if you assume that H1 of X is trivial, they can be identified with Hilbert schemes of curves on your threefold. In that case, the DT invariants are conjecturally related to Gromov-Witten invariants by the Maulig-Nekrasov-Okounkov-Pandharipande conjecture. Again, this conjecture also has a version without imposing the Calabi-Yau condition, but then one did some insertions. So kind of this was the initial theory in which we produce some integers via virtual fundamental classes. Okay. So next we categorify the story to certain vector spaces. So if X is Calabi-Yau, the DT invariants admit several refinements. The first one is you would like to write the DT, the numerical DT invariant, as an Euler characteristic of a certain complex of vector spaces. Actually, this complex of vector spaces is the hypercohomology of a certain sheaf on your moduli of objects on X, on the Calabi-Yau X. This sheaf is a pervert sheaf. So let's see where does this sheaf come from. So the point is that the stack parameterizing L semi-stable sheaves of a given support can be written as a critical locus. So you have a function f on a smooth stack. So here I don't necessarily assume that L stability equals L semi-stability. So no, then this object here is just a stack. So the statement is just that it's the critical locus of a regular function on a smooth stack U. In the L semi-stable equals L stable case, actually this space can be taken as a manifold. So on the critical locus, you have the critical locus of a regular function, you have some natural pervert sheaf besides the IC sheaf. You also have the vanishing cycle sheaf. So this is the relevant sheaf in Donaldson-Thomas theory. And so in this local case, for the critical locus of F, the relevant sheaf is the vanishing cycle sheaf. But in order to define this initial sheaf phi on ML alpha, one also needs the information of gluing. No, one needs to know how to glue these various sheaves coming from this local chart. So I won't go into that. And maybe relevant for later in the talk that one does not need to assume that X is proper. One can just look at compactly supported sheaves, still get numerical DT invariants and cohomological DT invariants. Okay, so why do we do this? Okay, so yeah, so maybe in cohomological DT theory, one studies this perverse sheaf phi. In DT theory, as I said, maybe the most relevant case is when L semi-stable equals L stable. But however, also the case when these two are different is important, and it appears in the study of quasiBPS on whole algebras. So next, I mentioned here a phenomenon called dimensional reduction. So what happens is if X is a local surface, so here S is a smooth surface, and you consider the moduli stacks of compactly supported sheaves of a given support alpha on both the threefold X and on the surface S, you have the following comparison between, on one hand, the vanishing cohomology. So here, maybe I should say that this phi over here, there is a canonical orientation data. So on one hand, you have some sort of vanishing cohomology. On the other hand, you have Borel morphomology. And of course, this isomorphism can help you, on one hand, in problems about the threefold geometry, in case the stack of objects on the surface is easy to understand. But in many applications, it goes the other way. So it's actually easier to study the Calabi-Yau threefold geometry. So here you have some information, for example, that this map, this sheaf phi is perverse, it has certain properties. Poincare duality. Then also in the L semi-stable, different from L stable case, you have a map from this stack to the core space. We can analyze push forwards along that map, get information about the supports of the sheaf there, and then via this isomorphism, transfer the information on the surface side and get interesting results about Borel-Moore homology of a surface. So for example, if S is C2, this is already maybe interesting. So on one hand, you'll have the moduli stack of points on C3, but with this perverse sheaf incorporated. On the other hand, you here MC2D will be the stack of length D sheaves on C2, which is the same as the stack of commuting matrices. Okay. So that's a very singular stack. It is contractible, so its singular cohomology is trivial, but here we take the Borel morphomology, which is not trivial. So then you might wonder about computations on that side. So this is an important tool in DT theory. So now I'm mentioning some applications of cohomological DT theory. They are also important in studying the structure of this quantitative whole algebra. So maybe I should just say a few words. So there are certain whole algebras defined again on the moduli stack of sheaves, and then multiplication is defined by the extensions of sheaves. So I'll define in detail an example later in the talk for points on C3. And the interesting representation theory is that these algebras are a vast generalization of positive halves of quantum affine algebras. Then anyway, one can study their structure, prove something like Poincare-Berkeley type theorem. So this is work of Davison and Meinhardt. More work of Davison showed certain positivity results about the quantum cluster algebras. Also, as I said, this the Borel morphomology of objects on the surface is well, it's kind of complicated because this stack is very singular. But by work of Deligne, it has a mixed Hodge structure. And actually, if you start with the K3 category and you look at objects in the K3 category, you can show that this Hodge structure is pure. So this is also work of Davison. Again, it uses this results about the Calabi-Yau threefold. Yes, it's two Calabi-Yau categories, but it has some other conditions, not exactly all of them. In general, yes, for all two Calabi-Yau categories is the purity about the push forward to the core space, and then in one needs some extra conditions to get it. But it's true for the example I was using. Yes. And also this cohomological DT theory has also applications in the topology of moduli of sheaves on surfaces. Del-Petzl surfaces, this is work of Malik and Chen, or if your surface is a local curve, so it's the total space of the canonical bundle on the curve C, it has it has also applications in that topology. So maybe here by work of Malik Toda, so Malik and Toda used the circle of ideas to propose the definition of Gopal-Kumar-Vafa invariant, also called BPS invariant. And they observed that the formation invariance of their proposed definition has to do with the P equals W conjecture. And this was solved by these authors. Okay, so next we would like to categorify this story further. So like the classical example would be to go from Betti numbers to singular cohomology, and then the categorification of singular cohomology for at least the smooth variety is given by the derived category of bounded complexes of coherent sheaves on X, and one recovers a Z-mod 2 periodic version of singular cohomology via periodic cyclic homology. So can we do something like this for DT invariant? So again, we have this numerical DT invariant. We went one step up, looked at cohomological DT invariants. Now the question would be to define a category, DG category, whose periodic cyclic homology recovers a Z-mod 2 periodic version of cohomological DT invariants. And then by taking the Euler characteristic of periodic cyclic homology, recovers the numerical DT invariant, and then study the structure of those categories. So yeah, maybe I should say we don't know how to do this in general. But a first case to consider is the local case in which you start with a smooth variety U with a regular function. And then you would like to categorify the cohomology of vanishing cycles. So this has been proposed, such a categorification has been proposed by Kontsevich and Soipelman in their article on whole algebras, and has been proved by Efimov. So such a categorification is given by matrix factorizations. And yeah, I'll define later matrix factorizations. So this is the local situation. Again, we would hope to define this general DT categories by gluing these categories of matrix factorizations. We don't know how to do that. We do not know what is an orientation data in this case. So what we can do in what we study are either some cases in which there is a global description of your relevant moduli space as a critical locus. Another situation is when the Calabi-Yau threefold is the total space is a local Calabi-Yau threefold. Then you expect to have, again, maybe a canonical orientation. You expect to glue these matrix factorizations. And then by causal equivalence, you expect this to be related to some categories on S itself, on moduli of sheaves on S. So basically, yeah, you take coherent sheaves on those moduli spaces quotient by some subcategories defined in terms of singular support. So then Toda proposed to study those some DT categories defined directly in terms of S. Okay, so So in categorical DT theory, one studies these categories in the cases they are defined. So here are a few directions of interest. So the first one is to obtain K-theoretic Donaldson-Thomas invariants, study them, do computations of those Donaldson-Thomas invariants. A related direction is sort of categorifying results that we already know about numerical DT invariants. So, there are some fundamental computations, see, do they hold at the level of homological DT theory, or do they hold at the level of categories? Do you have some interesting semi-orthogonal decompositions that recover those computations? Maybe an interesting direction here is, of course, the wall crossing. So when you change the stability, relevant stability condition. Another interesting one is the Donaldson-Thomas, Pandharipande-Thomas correspondence that I'll mention in the last part of the talk. So Pandharipande-Thomas are, yet again, some invariants defined using sheaves, and they are simpler to compute than Donaldson-Thomas invariants. So they are a more economic way of understanding the contribution of curves via sheaves. So they are also, it's also a more economic way of phrasing this sheaf to stable maps corresponds this DT to Gromov-Witten corresponds. So this is one direction of research. Another one is to understand the relation between DT categories and whole algebras. So, okay, so this, I said that this whole algebras appear when you have strictly semi-stable objects, and kind of the way you should think about them is that these are positive halves of some interesting quantum groups, but they should be vast generalization of the known quantum affine algebras. And then the DT category should be representations of these. So one interesting thing is make this precise or complete the categorical whole algebra to the full, to some full categorical quantum group. Another interesting direction of research here is both these objects are related to this Gopakumar-Vaha or BPS invariant. So the BPS invariants here, BPS invariants are sort of most fundamental enumerative invariants for which DT invariant or Gromov-Witten invariant should be computed. Then they have some nice finiteness properties. So here one direction of research is categorify BPS invariants, then decompose DT categories in terms of this categorification of BPS invariants. So this is like the sort of classical understanding of DT invariants in terms of BPS invariants. On the other hand, whole algebras themselves also have to do with BPS invariants. So what happens is that these whole algebras, they should be the positive parts of some quantum affine algebras, where the relevant Lie algebra is called the BPS Lie algebra. So, it's sort of a homological version of this BPS invariant. So this is number 2. And maybe to people interested in algebraic geometry, most interesting direction is 3. So use dimensional reduction. So I mentioned that sometimes, actually, in many cases, it's easier to work on the Calabi-Yau 3 side, get some results there, and then use this partial equivalence for dimensional reduction and move on the surface side and get some theorems there. And via this procedure, one expects to get results about more classical categories of coherent sheaves on moduli spaces on the surface, how matrix factorizations disappear. So some examples of results here are derived equivalence between moduli of semi-stable sheaves on a K3 surface for different stability conditions. So this is work, so here I should say that, and also stable equals semi-stable. So this is work of Halpern and Leisner, and it's work that checks the Kawamata-Bondel-Orlov conjecture in some very interesting cases. If you go one step down via dimensional reduction to curves, one can also construct semi-orthogonal decompositions of symmetric powers of curves. So some pieces will be Jacobians of curves, and some other pieces will be symmetric powers, but of smaller number of points on the curve. So this is work of Toda. So in this talk, we will focus on number one. So this is sort of intrinsic study of these DT categories. Okay. So as I said, we will focus on the case of points on C3. So this is maybe a basic example, but it's important. And for example, also appears in this DT-PT Donaldson-Thomas Pandharipande-Thomas correspondence. Okay, so what happens here? So the relevant space is the Hilbert scheme of points on of D points on C3. So this can be regarded either as quotients or as ideal sheaves on C3. So this X should be C3. We denote the corresponding DT invariant by DTD. So as usual, in this Calabi-Yau geometries, the relevant moduli space is very singular for D large enough. So it is not reduced. We do not know the number and dimensions of irreducible components. Maybe we regard this DT cohomology as a computable version of singular cohomology of Hilbert scheme of D points on C3, right? If we're interested in that, and just singular cohomology of these spaces, we have no idea to do that. Anyway, if we do this DT cohomology, there are many computational tools there. And we also regard this DT category that I still have to define precisely as a replacement of the category of DB-Co of Hilbert scheme of D points on C3. So this story regarding it like that is in stark contrast to the story for Hilbert scheme of D points on C2. So there, the Hilbert scheme of points is smooth, and one has many tools which are not available in the C3 case. But what I'll do is I'll first discuss the results about Hilbert scheme of D points on C2, and then I'll explain what the results have, analogous versions for C3. Okay, so let's look first for C2. We want to understand this the Hilbert scheme of points on C2. Maybe let's look at its topology. The most basic question would be understand its Euler characteristic, then move to understand its Betti numbers, then maybe move to understand its K theory, understand its derived category of coherent sheaves. So how to compute this Euler characteristic? Well, there is a two-dimensional torus which acts naturally on C2. This also induces an action on the Hilbert scheme of D points on C2 that we regard as parametrizing ideals I of the structure sheaf of C2, so which are polynomials in X and Y, let's say, of co-length D. Okay. So we want to see, so the Euler characteristic of Hilb is the same as the Euler characteristic of the T fixed locus of Hilb. Actually, this fixed locus is just a bunch of points. Okay, so the invariant ideals correspond to ideals generated by monomials, xi, y to the j. And there is a correspondence between such ideals of co-length D and partitions of D. So what you do is in the first quadrant, you take the complement of all pairs ij such that xi, yj is in your given ideal. And then, yeah, the complement in the first quadrant is a shape like that, which corresponds to a partition of D. Okay. So I denote the number of such partitions by P2D. And then the Euler characteristic of Hilb C2D is just this P2D. So this is a very basic computation. Then you can ask for Betti numbers. And then, so here, because Hilb C2D is smooth, you have Bialy-Nicky-Birol decomposition given by certain attracting loci for a generic C star inside the torus. So the point is that you get a stratification of the space by affine spaces, CA. And then the question is, can you count how many times C appears in this cellular decomposition? And this was done by Ehrlich and Strome. And such a computation gives you an answer for the Betti numbers of Hilb C2D. Okay. Another direction in which you can go is study the Göttingen group. So then this is actually easier in this case than computing the Betti numbers, because you have a certification, you know that you have P2D strata. So the good by standard computations in K-theory, you get that the Göttingen group is a 3Z module of rank P2D, the number of plane partitions. So maybe a question now going to the derived categories is you have the category of coherent sheaves on Hilb C2D. Well, can you understand this isomorphism in terms of that? So such a theorem that provides such an explanation is this Bridgeland-Kingread that tells you that there is a derived equivalence between Hilb C2D and an orbifold. So where the orbifold is C2 as a power D mod sigma D. So sigma D is the symmetric group on D letters that acts naturally on the D power of C2. So we would like to do something similar for Hilbert scheme of points on C3. So yeah, we would like maybe understand the Euler characteristic, understand the Betti numbers, understand the derived category. As I said, it will be too hard to do, especially the Betti numbers and the derived categories for just Hilb C3D. So instead we use this DT theory. So then the first question is compute the numerical DT invariant. So actually just a computation as before gives you the Euler characteristic of Hilb C3D. So again, you have a torus acting naturally on C3, acting naturally on Hilb C3D. Then the fixed loci will be given by ideals of polynomial rings in 3 variables generated by monomials. Again, if you take the complement in the first octant of the set ijk, such that the relevant monomial is in the ideal, you obtain such a shape, which is called the 3D or the plane partition. Okay, so then you have that the Euler characteristic of Hilb C3D is the number of 3D partitions of D. So a similar answer is also given by the numerical DT invariant, but this is a theorem of Berendt-Panteki, so one also has to deal with this vanishing cycle imposed there. Okay, so then one can ask whether there are formulas for the singular for the DT cohomology, and there are indeed, one can compute analogous formulas to those in dimension 2, and this was done by Berendt, Bryan, Sandor, and Davison. So now I'll explain how to define this sheaf phi. So in particular, this will explain how to define this cohomology spaces, and by taking the Euler characteristic, you also obtain a definition of numerical DT invariant. So what happens in this case of D points on C3 is that you have a global description of your moduli space as the critical locus of a regular function on a smooth space. So indeed, we'll write this Hilb C3D as the critical locus of W, where W is a regular function on n Hilb D. Okay, so how can we do that? Okay, so let's try to describe the Hilbert scheme of D points on C3 via some linear algebra. So let V be a vector space of dimension D, and then the scheme Hilb C3D parameterizes. Now we look at quotients instead of ideals. Quotient of the structure sheaf of C3, so C, X, Y, Z, and the quotient of length D. So how can we understand this? Well, we let lowercase v be an element of the vector space, which is the image of 1 of the identity of the polynomial ring. Then the generators x, y, z induce endomorphisms of v. So then we have a tuple lowercase v, x, y, z in v times the endomorphisms of v, the power 3. So let's see, what properties do this endomorphism satisfy? Well, they come from the generators of a polynomial ring, so they will pairwise commute. This is one condition. We also now have to use the fact that this map from polynomials into V onto V is a surjection. So this condition is the same as saying that lowercase v generates the full vector space under the action of x, y, and z. Okay. So this is a description using linear algebra. The condition that introduces singularities is this pairwise commutativity of x, y, and z. So we eliminate this to get a smooth space. So let n hilb d be the smooth variety, which now parameterizes tuples lowercase v, and then three endomorphisms x, y, and z. And the only condition is the generation, the surjection part. So lowercase v generates the full vector space under the action of x, y, z. And now what happens is that this variety can just be described using a GIT stability for determinant character of GLV acting on this space. And then this semi-stable locus ends up being a variety, just a stack. So we end up with a smooth variety. Now we still have to impose this pairwise commutativity conditions. So as I said, yeah, the kind of fundamental thing in this Donaldson-Thomas theory is that these spaces are critical loci. Okay, so we need to produce, and well, there is a function on this non-commutative Hilbert scheme whose critical locus will end up being the Hilbert scheme of points on C3. Okay, so what is this function? It's the trace of x times the commutator of y and z. Okay, so you have this function on n hilb d. Then you can imagine that we expand it in the coordinates of x, y, and z. Then you have to impose that the partial derivatives with respect to the x coordinates, all these partial derivatives are 0. And this will say exactly that the commutator of y and z is 0. So you get that y and z are 0. Well, but then by permuting the x, y, and z in the expression of w, you get that up to a sign, w is also trace of y times the commutator of z and x. You do the same argument using the partial derivatives for the y coordinates. You also get that x and z commute. You also get that x and y commute. So they all pairwise commute. So indeed, it happens that the critical locus of w is exactly the Hilbert scheme of d points on C3. Okay, so we have this description. So now we have our relevant perverse sheaf. So you start with the IC sheaf on n hilb d. Okay, so this n hilb d is just smooth. So IC sheaf is just a shift of the constant sheaf. You don't have to worry about that. And then you take vanishing cycles with respect to this function. You'll get a perverse sheaf on hilb C3d, and this is the relevant sheaf that the one studies. So now, as we saw, there are results about numerical DT invariants and results about the homological DT invariants, which parallel those for the Hilbert scheme of d points on C. So we would like to see if we can say the same thing about the categorical version. So let me first mention the definition. So as we said, categorification of vanishing cohomology is given in the local case, is given by matrix factorizations. So the relevant category here is matrix factorizations on n hilb d for the regular function w. So the objects of this category are tuples as follows. So you have E and F coherent sheaves on n hilb d, and alpha and beta are morphisms such that both compositions alpha beta and beta alpha are multiplications by the regular function w. So the plan is to study this category DTD on its K-theory. Okay, so we still need one ingredient before I start mentioning the main results. So it's the whole algebra of points on C3. So the relevant spaces should be the moduli stacks of points in C3. Those can be also described using a critical locus. So actually what one does practice is one starts with representations of the free loop weaver. So alternatively of this algebra, the free algebra on XYZ. So you do not impose commutativity. You will impose the commutativity comes by when you impose this matrix factorization condition. So the categorical whole algebra of C3 is a monoidal category. So the graded pieces are matrix factorizations on XD. So on these stacks that are just some affine space mod GLD for the function W. So W, again, if this GLD has elements capital X, capital Y, capital Z, W is the trace of X times the commutator of Y and Z. So the critical locus of W is exactly representations of polynomial algebras. So you get torsion sheaves on C3. Okay, so this is the underlying category. And how does one define multiplication? So in whole algebras, one defines multiplication via extensions of objects in your space of interest. So here you start with two-dimensional vectors XD and, this should be E. Then you have a stack parametrizing extensions. So here, for example, pairs A and B of representations of dimensions D and D plus E. And then you have, forget the sub-representation map to XD plus E. And then there is pullback, there is push forward. These potentials are compatible along these maps. So one gets a product on these categories of matrix factorizations. So this will be the whole algebra of the point. Okay. So now let's look at the first results about DT. This
here assign some functors.
Yeah, so the functors are these M's. Yeah, so you need properness to define push forward along P. For matrix factorization, but the map P is proper from the stack X.
What's happened to the function when you define we use finish the problems.
Oh, but
the function.
Yeah, but if you have a proper map between two stacks and X and Y, and you have regular maps, you have the push forward. So this is Polish confined. And similarly, you also have pullback, but you don't need to assume properness for pullback. Yeah, you just need the stacks are smooth, or the ambient stacks X, Y are smooth. So so we would like to study this DT category. So let's go back to Hilbert scheme of D points on C2. That category is indecomposable because Hilbert C2D is Calabi-Yau. Oh, maybe a natural first guess would be that a natural first question is whether this DT category is also indecomposable. If it's not indecomposable, then find the semi-orthogonal decomposition in indecomposable pieces. So this is our first result. So we construct a semi-orthogonal decomposition. So there is a certain data here, but in pieces that we believe to be decomposable. Okay, so what happens here? So the relevant pieces are these categories SDV that we call quasi-BPS categories. So they depend on D, the number of D points, and there is some extra weight that appears here that did not appear in the homological picture. There is this integer weight V. And then the pieces in the semi-orthogonal decompositions are whole products. So this is like, okay, so I'll make it more precise, but comes from the whole product that was defined on the previous picture of this that we believe to be decomposable pieces. And then there is some combinatorics in which weights are allowed here to be part of the semi-orthogonal decomposition. Okay, so up to showing that these quasi-BPS categories are indecomposable. This would answer the first question. So now I should explain what is the definition of these quasi-BPS categories. Then also why do we call them? What's the relation with BPS invariants? As I said, go back to normal invariant. Okay, so how do we define these categories? There are certain subcategories of matrix factorizations on the stack with potential W, where the matrix factorizations, so matrix factorizations were two sheaves, E and F, with two maps, alpha and beta, such that compositions in both ways is W. We want both factors E and V to be in a certain category MDW, that I still did not define. And this category MDW, these categories are twisted non-commutative resolutions of the core space XD of the stack, currently XD. So that was the relevant stack when defining the whole algebra, constructed by Spenko and Vandenberg. Okay, so maybe I should, so why would one guess that something like this works? So kind of in this categorical story, similar to the cohomological one actually, is that if one proves statements categorically enough, one can assume that the potential is zero. So then the relevant space here will be coherent sheaves of the stack XD, which is a very nice smooth stack. So it's just an affine space mod GLD. Then you would like to decompose this space. Unfortunately, there are many techniques on the market. So in the last 10 years or so, many people worked in decompositions, semi-orthogonal decompositions of stack. So Halpern, Leisner, Ballard, Favero, Kavtsarkov. I guess maybe everything started with Ed Siegel, Halpern, Leisner, Sam, Spenko, Vandenberg. But the work of many such papers is about variation of GAT. So here it's kind of a rigid case. You don't have interesting GAT conditions, but you can still use inspiration from those papers, and especially this paper of Spenko-Vandenberg that deal with cases beyond variation of GAT, to find semi-orthogonal decompositions of those stacks in which the pieces are as small as possible. So of course, ideally, you would like those pieces to have to do with this BPS invariant. However, that might not be the case. Those categories might be larger in a sense than BPS invariant, and they might be indecomposable. So kind of this category, you should think of this category as MDW is, they are sort of smallest categories of DB of the relevant stack, XD, that one can define using the techniques on the market. Okay. So the precise definition is as follows. So let's take the simple roots of GLD, beta 1 up to beta D, and let the rho be half the sum of positive roots of GLD. And this category, MDW, is defined by explicit vector bundles. So it's the structure sheaf of XD tensor, irreducible representation of GLD of highest weight chi. And now chi has to be in a certain polytope. So chi plus rho, and then W appears here. So you sort of shift by this weight. And then it has to be in this Minkowski sum of weights. So this would be inside the weight space of PGLD. Anyway, this is the precise definition. As I said, if you haven't seen the stuff before, maybe you should think that these categories MDWs are just the smallest categories we can define using the techniques in these papers that I mentioned. Okay, so now how does this whole product appear in the non-commutative Hilbert schema? So there is a natural projection by forgetting the lowercase v, the image of 1. And then the theorem follows actually from the zero potential case. So then one should show a semi-orthogonal decomposition of dB n Hilb d in pi upper star of whole products of these categories of this twisted non-commutative resolutions. And then okay, so here we have to understand what types of weights we allow. Okay, and then there is this slope type condition that we get. So again, this technique uses variation of JT. So now N hilde D is constructed as a JT semi-stable space. So you can realize it inside dB of a stack, V times GLD and the power 3 mod GLV. And yeah, you can use the techniques of these authors. And then, basically this decomposition boils down to decomposition of polytopes inside some weight spaces. But then kind of the hard part is the understanding the combinatories, what polytopes, in which smaller polytopes you decompose the larger polytope. And this is how this condition, these weights come in. Okay. So next, we have this semi-orthogonal decomposition for the DT category. We would like to understand its K theory. So then the first step would be to understand the K theory of this quasi-BPS categories SDW. So what we can do now is use dimensional reduction. So go in the dimension to case, then try and do computations there. So the important theorem here is a theorem of Isik, this also called causal equivalence, that says that graded matrix factorization on XD with potential W. So maybe, yeah, so this is some other version of matrix factorizations, but for computations in K theory, it's not that important. It will have the same Grothendieck group as the matrix factorizations defined previously. That this category of matrix factorization is equivalent with coherent sheaves on the stack of pairs of commutative matrices of size D. And then by previous work on whole algebras, these categories SDW, these quasi-BPS categories, are admissible inside this stack. So this is this phenomenon that I mentioned at the beginning. So this BPS invariants are most fundamental pieces for which you build DT categories. So you have semi-orthogonal decompositions of those, but also most fundamental pieces for which you build the relevant whole algebras. So in this case, yeah, the whole algebra of points on C3, this is a categorification of positive part of elliptic whole algebra, but it also has a decomposition in whole products of quasi-BPS categories. Okay, so we can realize these quasi-BPS categories inside this stack CD. Okay, so why would that be important? The point is that there are some tools in K theory to analyze this category now. So now, yeah, so for about this question in K theory, ideally, we would like to understand the K theory of these quasi-BPS categories, but this seems to be too hard of a question right now. Then there are two ways to make it a simpler question. You either go to equivariant K theory, then you can even make it simpler by localizing everything. Okay, so then you'll just get some vector spaces. So this is what we do here. So with uppercase K is a representation, a ring of T, and F is its fraction field. So we will localize and do computations over the fraction. Another direction in which you can make things simpler is use topological K theory. So yeah, for simplicity, I'll discuss the case of equivariant K theory. And now we have a map from the stack CD, the stack, to the stack of pairs of matrices, so without imposing the commutativity condition. And we construct certain objects EDW with explicit shuffle formulas under this map that will generate equivariant K theory of these categories. So here, it's important to, so we use some inspiration from this BPS spaces. So we know that the BPS cohomological spaces are supported over the small diagonal. So this is some work of Davison. So then we look for certain objects here that actually come from the stack of pairs of commuting upper triangular matrices where all the eigenvalues are equal. So then let's fix coprime integers D and W, and then we okay, so via this stack of upper triangular matrices with equal eigenvalues, we can produce natural objects. And then what happens under this shuffle algebra is, is that we recover formulas of Negwitz. So Negwitz and other people in representation theory extensively studied this whole algebras. And then they have many structure theorems. So using their results, we can understand the localized equivariant K theory of these categories. So this is the theorem. So maybe, okay, so it has a basis. In particular, its dimension over F is the number of partitions of N. Okay. And then when N equals 1, we regard this category SDW as a categorical version of BPS invariants of D points on C3. So an example is this numerical computation. So the BPS invariants are for points on C3 are all equal to -1. And then via some wall crossing results, you can get that the DT invariants are up to assign the number of plane partitions of D. Okay. So what happens here is that the K theory of this quasi-BPS categories is too large if the greatest common divisor of the number of points and the weight is strictly bigger than 1. But if they are co-prime, you actually get 1. And then you can ask, well, do they satisfy some properties similar to BPS sheaves, things like that? And the answer is yes. So a fundamental, as I said, a fundamental result is the support lemma for BPS sheaves, which categorify as BPS invariants, that they are supported over the small diagonal in XD. And also complexes in quasi-BPS categories SDW, when the greatest common divisor is 1, have elements supported over the small diagonal. But then what happens in the categorical world is, well, if you have this ND, NW situation, there's nothing you can do. So they are not categorification of BPS invariants, but we also believe that these categories to be decomposable. So you just have more things in the categorical world than in homology. You have to study them independently. But what happens is if you pass to K theory, there is a coproduct map, at least in the, so actually there is a localized, there is a coproduct map in the general case, also in the categorical world. And, but still, you can define this K theoretic BPS invariant, BPS spaces as primitive elements with that coproduct. With respect to that coproduct. And then you can get, so you have a definition of K theoretic BPS spaces. And even when the greatest common divisor of points and weight is not 1, you still recover that at least the dimension of this localized equivariant K theory is 1, which is the absolute value of BPS, invariance of D points. Okay, so this is, so again, in this categorical world, if the greatest common divisor is 1, we get some pieces that are like BPS invariants. But if the greatest common divisor is not 1, we just get some new phenomena. Okay. But using this two theorems that I mentioned, we recover a K theoretic version of Berendt-Fantegi computation. So as I said, maybe some first problems in this categorical DT theory would be compute K theoretic invariants, see how they compare to the cohomological invariant. You know, and then yeah, an important problem is, can you see this number of plane partitions? And indeed, the dimension of this localized equivariant K theory is the number of 3D or plane partitions. Okay, so I also want to say a few words about applications of these theorems beyond this Hilbert scheme of D points on C3. So they are in this Donaldson-Thomas, Pandharipande-Thomas correspondence. So Pandharipande-Thomas are certain invariants defined via moduli of stable pairs. So now stable pairs are certain complexes OX with a map to F, where F is torsion-free and the co-kernel has support of dimension at most 0. So you should think that these stable pairs, they are like a curve, you know, C, which is given by the map of this section S, and a bunch of points on the curve C. So they are more economic than DT invariants. In DT invariants, you would allow a curve C plus points which are somewhere on X, but not necessarily on C. Anyway, one can define this invariant, Pandharipande-Thomas invariants, again, using virtual fundamental classes. Actually, they also have this description using critical loci, so one can also define them by vanishing cycles and things like that. And why are they important? They appear in the statement of the MNOP conjecture. So this was the conjecture relating Gromov-Witten, so this stable maps invariant with sheaf invariant. So basically, yeah, what they say is that this DT invariants for support beta and other characteristic n are a sum where here you have Pandharipande-Thomas invariants of support beta and n minus k times DT invariants of points on your Calabi-Yau threefold. That, you know, locally they should behave like points on C3, which was the main topic of previous results. However, we do not have a definition of even DT categories of points on an arbitrary Calabi-Yau threefold. We just have it for a local surface. Then we can wonder if there is a categorification of the DT-PT correspondence. Okay, so maybe, yeah, before I move on, so this is a very important theorem in enumerative geometry, and it uses a lot of deep work. So the final proof was given by Bridgeland, but it uses machinery developed by Joyce and his collaborators, and by Kontsevich and Sobolman on wall crossing and motivical algebras. So yeah, there's a lot of work gets into proving something like that. We would like to understand it, a categorical version of it, and preferably give a simpler proof. But of course, as I mentioned, there are some technical difficulties involved in just starting the problem defining these DT and PT categories. There is also, we will also want to push forward stable pairs or certain pairs from the threefold onto the surface. So, and yeah, stable pairs on the threefold onto the surface. And still have them stable. So then we need to impose some conditions on beta as well. So we have that beta is a reduced class, but we can just also assume that beta is an arbitrary class and work over the reduced locus. So we obtain a semi-orthogonal decomposition like this that kind of parallels the numerical DT-PT correspondence. So indeed, so these are some quasi-BPS categories for points on X on the local surface. So now, if you take K theory and if you combine some of the sort of first theorem that I mentioned in this talk, but for a local surface, you get a K theoretic version in this just particular case of the DT-PT correspondence. So the K theory of DT categories decomposes as a sum of K theory of products of DT categories of points and PT categories. We cannot use the Kuhn formula here, so you cannot simplify it further. So yeah, maybe the last minute. So how does the proof go? So these DT PT spaces are related by a wall crossing for a certain stack of maps OX to F. But now you don't assume that F is pure. And then, okay, so this stack has a good moduli space, and you would like to understand both the space, both the DT, so DT has to do with ideal sheaves, PT with stable pairs. You want to understand this locally on this core space. And the point is that locally they have a description using quivers with potential. So then locally these DT-PT categories are given by matrix factorizations on certain spaces, on certain semi-stable spaces on a representation space of a quiver. So then you want to show the statement locally. You can just show the case when the potential is 0. So again, it's a variation of JK problem. Yeah, that's all.